Okay, so we had finished up kind of the last couple days talking about delta H and measuring heat and energy changes in systems. And what we're going to see now is do a couple calculations or use it to do some various types of problems where we'd want to know about the energy generated in a chemical reaction. And then we'll also start looking at how we calculate or where we can get all these delta H values from that we would want to do problems. And so it's kind of two different things that are related basically because they're about delta H. So first thing we want to do is talk about what we call the standard state. And we give that a special symbol. It's a little circle up on top, so it's the superscript, and what that simply means is the standard state. And it means that we use the most stable form of the substance. If you look at the appendixes that I printed off, or obviously the ones in your book, most stable form of a substance, what you'll see is that they have a huge list of chemical compounds in there. And for some elements, there's more than one form that those elements kind of occur naturally in that are related to each other. And so the standard state says use the most stable form of that substance. We are always at 25 degrees Celsius. So if we do a reaction at any other temperature, then some of these values will change by small amounts. Usually, you know, as long as you're plus or minus 5 degrees, if you're basically at room temperature, it's not going to make a difference. For liquids and things, we need to have a 1 molar concentration. And then the other one is we need to be at 1 atmosphere. So obviously, if we're doing things in Rangeley, it's a little bit different. And one thing I should note here, that technically they've redefined this, but it's, again, such a small difference that anything we're doing, we're going to get more error just by rounding numbers probably, to 1 bar, which is technically 0.986923 atmospheres. And so really that's actually better for us because, you know, we really are above sea level, so we really are below atmospheric pressure. So the standard state is really just saying use the right values, and that if we have to do any calculations that are different from those values, then we have to take that into account. Now we will look at the effect of temperature on reactions second semester when we're talking about kinetics. We will look at PV equals nRT for doing some calculations on chapter 9. And then the concentration one, we probably won't run into anything with that until we do electrochemistry way at the tail end of second semester. So we don't have to worry about it too much. The other thing we have to remember about delta H values is we have to be very careful of the states. So the physical states of things are important. And the reason that the physical states are important is because it takes energy to go from one physical state to another. We know that in order to go from, say, solid ice to liquid water, what do we have to do? We have to add energy, right? And so if we have a reaction that uses solid water, but we really have liquid water, and we want to know what's going on in that reaction, then we have to realize that we have to, you know, go from liquid to solid and then do our calculation. An example of that is really probably the most common one is H2O liquid going to H2O gas, where delta H naught is 44.0 kilojoules per mole. So, you know, if we have something in the liquid state and we want it to be in the gas state, then we have to remember to basically subtract off 44 kilojoules per mole. Now, is this reaction as a test endothermic or exothermic? 50-50 guess. Is this reaction endothermic or exothermic? Yeah, it's endothermic. Why? There's two reasons. And the easiest one is probably to simply say that delta H is positive, so that means it's endothermic, right? The system absorbs energy. The second one is we know it takes energy to go from a liquid to a gas, right? If you're boiling water, essentially, that requires an input of energy into the system. So we can say it's endothermic from that, too. The other thing that we have to realize is that direction is important. And so you have to be very careful kind of when you're looking at what values you're looking at and also what values are written in the book. Because, for instance, if we do the opposite of the above and you're not paying attention, you know, if we're going from a gas to a liquid, well, delta H in the opposite direction is, of course, just the opposite value. And so if you're not careful and you use plus 44 kilojoules when you should be using minus 44 kilojoules, then it's going to be problematic. The other thing is to realize that these are molar quantities. So if we're looking at reactions, for instance, where, and this is a silly example, but say 3 waters are converted to 3 water molecules in the gas state, then our delta H naught value is 3 times that 44.0 kilojoules because it's kilojoules per mole and we've got 3 moles. So kind of be careful with states. Be very careful with the direction that the reaction is actually going and use the right value for that, positive or negative. And then if we're using molar quantities, remember that we have to multiply it by the moles. So let's look at an example. And I think we did a similar example yesterday, but I don't remember, so we'll just redo something similar. How much, I think this example is actually simpler. How much heat is released when 2.50 moles of NO gas react? And the equation we've got is 2NO gas plus O2 gas goes to 2 NO2 gas. And we know that delta H for that reaction, or basically the energy change, is minus 114.6. That's why I think it sounds familiar. I swear we used that value yesterday. So what do we want to do here? So our question is asking us how much heat is released when 2.5 moles of NO reacts. So what we're really saying is we want, you know, if we kind of think about it in that question-answer format, our answer says how much heat. Well, we know that that's in joules or kilojoules. You know, we're not too picky. And then where do I start this reaction? Well, the only piece of information I know is 2.50 moles of NO. And so what we can realize is that delta H values are really just conversion factors between moles and temperature. So we know that 2 moles of NO produce minus 114.6 kilojoules. I'm sorry, kilojoules per mole. There we go. And so it's just 2.5, or it's 114.6 kilojoules per, 2 moles. And so we get minus 143.3 kilojoules. So what we want to realize is that this value here depends on the number of moles written in that reaction. And so really it's almost like having a mole-to-mole ratio, or it's kind of like having our molecular weight grams to mole. We can now have sort of a kilojoule to mole ratio. So it's just one more conversion factor that's kind of thrown into our chemical reactions. Gabe, are you working on physics homework?
Yeah.
It's okay. I guess I'm taping this. You can watch it later is the theory.
Oh, yeah.
Nathan, what homework are you working on? Oh, that's good. At least it's the right subject. Okay, so we can use those delta H of reactions, and the most common use is to simply find out how much energy is needed or used or produced if it's an exothermic reaction in a chemical reaction. Now the question is of course, where do all those delta H values come from? The easy answer is table B in the appendix. So a bunch of them are tabulated, but it turns out that, you know, that is only a couple hundred reactions maybe. And instead what we want to do, and I think I have appendix A written, it must be a different version of the book, they moved the appendix. What we realize is that's only going to work for a very limited case. So we've got several methods where we can calculate it. The first method is to use what are called enthalpies of formation. Or when we write it, of course, you're going to use the abbreviation delta H naught F. And so remember that subscript means standard state. And now when we add a superscript F, that's just talking about formation. And what it really means is that it's the heat change when 1 mole of a compound, when 1 mole of a compound is formed from its elements at a pressure of 1 atmosphere. So heat change when 1 mole of a compound is formed from its elements at 1 atmosphere. So what it is it's a tabulation of chemical compounds that we know how much energy it takes to make them. And if we know how much energy it takes to make them, then if they change in a chemical reaction, we know that the change from one compound to another, energy is conserved, and so we can calculate any missing parts we want. We should note that it's an arbitrary point, meaning we don't do calculations as long as we have it. It's kind of like the idea of saying that sea level is equal to, 1 atmosphere. We could have picked and said, well, since we did almost all scientific discovery in Rangeley, that, standard temperature and pressure meant, 0.98 or 96 or 97 atmospheres like it is in Rangeley. And so it doesn't really matter what the zero value is, because remember, the only things we ever measure are changes. And so what we can say is that the change in the delta H of reaction is simply equal to the change in the enthalpy of formation of my products minus the change in the enthalpy of formation of my reactants. Or basically, the change in energy in a reaction is simply the change in energy in all of the physical parts of a reaction. So let's take a look at an example. If I have the reaction 2 aluminum solid plus Fe2O3 solid goes to Al2O3 liquid plus 2Fe liquid. And so what you do is we look in Appendix B for all of those values. And so if I look it up, aluminum solid is 0. And I should point out that all elements in their pure state are 0. That's that arbitrariness of it. We can simply define the delta H of formation of an element in its most stable form as 0. And then if we measure the formation of another compound, then all we care about is the change anyway from those basic elements. If I look at iron 2 oxide, iron 3 oxide actually, it's minus 824 kilojoules per mole. Al2O3 in the appendix is minus 1676 kilojoules per mole. And then I have to be honest, this is kind of a crappy example. Iron liquid, since it's not its standard state, meaning it's not a solid, we have to look that one up, and it's really just 13 kilojoules per mole, meaning it doesn't take much energy, or it doesn't take much to change from a solid to liquid for iron. This is not in the appendix. I think I just Googled it in the end. And so what we're saying is that the delta H of reaction is simply equal to the delta H of formation of the reactants, or the products, I'm sorry, products minus delta H naught of formation of the reactants. And so, for instance, I have 2 iron liquids, so I need to take 2 times 13, or 2 moles times 13 kilojoules per mole, plus a minus 1676 kilojoules per mole, because there's 1 mole of aluminum oxide. So there's my products. And then I need to subtract off my reactants. Well, 2 moles of aluminum is easy because aluminum is just 0 kilojoules per mole. And then plus a minus 824 kilojoules per mole times 1, because there's only 1 mole of the iron 3 oxide. And then it's just simply solving that math equation. You guys are good at math. You get minus 1650 minus a minus 824, and you get minus 826 kilojoules per mole. So that means the reaction is exothermic. And if you guys remember, this is just, now I'm going to forget it. Nathan will remember for me. What's the one where we mix aluminum and iron oxide? Thermite. That's it. This is just our thermite reaction. And so we know thermite is an exothermic reaction. We did it in the hood. We made a bunch of big sparks and everything like that. And we notice that when we do the calculation, we get minus 826 kilojoules per mole. Now, one thing that I want to point out is that we should always use our common sense when doing these types of questions. Meaning, if we know our reaction is exothermic, you do the process or you do the problem and you get an answer that's positive, you've got to stop and say, I either mixed up my signs throughout the entire problem and I just need to add a negative sign in it maybe, or you need to go back and look through that problem and go, okay, I know it's got to be exothermic because all combustion reactions are exothermic, and so you better figure something else out. Okay, so delta H's of formation are wonderful. But again, our appendix only has maybe a couple hundreds of examples. Well, frankly, there are about 30 million known compounds. And we only know the delta H's of formations for a few of those. And so if we want to do any sorts of calculations to see if things are feasible, if a chemical reaction is likely to occur or not, we need to use some approximations. So the second method that we can use to calculate the delta H of reactions is we use bond dissociation energies. To approximate the reaction. And here we have to be very careful. Our equation is that the delta H naught of reaction is equal to the bond dissociation energy of my reactants minus the bond dissociation energy of all my products. Because of the way we're defining bond dissociation energies, we take reactants minus products. Now, in the other one, when we're using delta H of formation, we're taking products minus reactants. So it's very easy to mix up and forget and do one of the two backwards, or I've even had people flip-flop both of them, in which case all of your answers tend to have the wrong sign in it, and it's kind of annoying. So we're going to take a look at an easy reaction first, one that doesn't involve breaking and breaking too many bonds. If I take nitrogen gas plus 3 hydrogen gas, I can react it together to form 2 NH3 gases, or ammonias. And I should point out that this is on, oops, I put it on the last slide. All your bond dissociation energies are actually on page 225 in table 7.1. So notice we're in chapter 8, but we're using all this information from chapter 7. I did print these out. The printout's right in front of your bag, Gabe. If you don't want to carry your book around, then at least, grab that table and go ahead and do that. Or if you just carry your book around, then don't bother taking the table. You've always got your book with you. So, if I take a look at it, we need to kind of look at the chemistry that's going on. For instance, I have to see what bonds I break. So for nitrogen, I need to break apart that nitrogen triple bond. And so if I look that up in the book, it's 945 kilojoules per mole. And then I also need to break the hydrogen-hydrogen bonds. And if I look that up in the book, it's 436 kilojoules per mole. And then I take a look at the molecule NH3. Notice that it's got 3 bonds to hydrogens. And so I need to make 3 bonds between nitrogen and hydrogen. And if I look that up in the book, it's 390 kilojoules per mole. And then the other thing to remember is that I've really got 3 moles of hydrogen and 2 moles of ammonia. And so what I'm really doing is I'm taking 1 mole of nitrogen, 945, plus 3 moles for the hydrogen. I'll just actually write it like this. That way we can at least see kind of where the numbers are coming from. And then we subtract off 6 times that nitrogen-hydrogen bond strength. So basically it's 1 times 945 plus 3 times, can't read my handwriting, 436 minus 6 times 390. Again, it's all math. You guys are pretty good at math. When we end up finishing the math, we get our delta H naught of reaction equal to minus 87 kilojoules. And we note that that's reasonable. And if we compare that versus the delta H naught of formation from the book, then we get minus 92.6 kilojoules. And so we notice there's about a 6% error doing this. And for a back-of-the-envelope calculation, for something that you would do just to see if something's likely feasible, a 6% error probably doesn't matter. That's good enough in most people's books. We can do a slightly harder one. And I don't know, are you guys even following along? This one's harder in that there's a lot more chemistry going on. A lot more bonds being broken and stuff. You have to actually balance the reaction. And so, if, you know, this is a more complicated example, but it shows all those features. So this is basically the combustion of butane. And butane is commonly found in most lighters, and so it's something you might come across. And so what we have to realize is that in order to figure this out, the first thing we have to do is balance the reaction. So this is good review from chapter 4. And I'm going to balance it. It's 2, 13, 8, 10. And then what we have to do is we have to say we want delta H naught of the reaction, remember, is the bond dissociation energy of my reactants minus the bond dissociation energy of my products. And so here's where we have to take a look at it. For instance, if I take a look at the molecule CH4, I almost have to draw the Lewis structure of that molecule, or C4H10, sorry, then in order to see what I'm doing. So here's my Lewis structure for butane. And so see, this is also good review because this is a review of Lewis structures, which, you know, we just had in the last chapter, so hopefully it's familiar. So if you take a look at it, I've got 2 molecules of C4H10, and I've got to break 3 carbon-carbon carbon-carbon bonds because I need to break 1, 2, 3. And then if I look at it, I've got also oh, I'm sorry, I'm doing this backwards. Whoops, we need to do reactants minus products. Why do I have... Oh, I see, I just wrote it funny. So I've got 2 molecules, I've got 3 carbon-carbon bonds to break. I've got 2 molecules, and because there's 10 carbon-hydrogen bonds, I've got 10 of those bonds to break. And then I've got 13 oxygen molecules that I have to break, so that's breaking OO double bonds. And then I can subtract off, and see again, I need to know what CO2 looks like, so we can draw it. It's got double bonds to oxygen. And so I need to make 2 molecule, or there's 8 molecules, and each molecule has 2 carbon-oxygen double bonds. And then for the water, to make that, I have to realize that I need to make 10 waters, and each water has 2 oxygen-hydrogen bonds. And then, of course, if I go look the values up, that's 350. This is 410. This is 498. This is, oh, sorry, forgot to put brackets. Remember, we have to subtract that from all of that. Carbon dioxide or bonds are 732, and OH bonds are 460. You skip all the nitty-gritty, gory math in between because that's just math. We get delta H of reaction equals minus 4138 kilojoules. And we notice it's negative because this is combustion. Makes sense. We know that H, or the energy, is a product, or the heat is a product. And if we compare that versus the value in the book, we get that it's delta H of combustion for this compound is 287 or 2,877.5 kilojoules. So our answer seems very far off until we realize that the way the value is reported in the book is that's per 1 mole, but notice our value is for 2 moles of C4H10, and so if we divide our value in half, we get 2069 kilojoules per mole. It's still pretty far off, but such is life. You know, what we probably really have to do is we have to realize that we convert water from a liquid to a gas. We're cruising right along because no one's stopping and asking questions. It's kind of refreshing. So another way that we can look at enthalpy in chemical reactions is called Hess's law. And what his law basically says is that the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes for individual steps. And really what we're looking at is this is essentially the exact same thing as a Bohr-Haber cycle. I know how much you guys loved those, so I'll probably put one of these on the test, except these are a lot easier because the states and things like that are easier to figure out usually. The reason we can do this is that we also know that delta H is really a state function. So it doesn't matter what path we pick to do all the chemical reactions. The only thing that matters is that when we add it all up, the reactants and product sides are the same. We don't care how many individual steps there are. So the idea is that the overall change in enthalpy is equal to the sum of the individual enthalpies. These of reactions for individual steps. Or really what we're saying is that delta H of reaction is equal to delta H of the steps, the sums of them. There are 5 rules that we need to know to kind of keep track of. And we've already looked at some of these rules when we were just talking about things. But in general, when we're doing things, reactants always appear on the left. It seems like a very simple rule, but the idea is that when we have reactions, remember, they flip. And we can write a reaction in the forward direction or reverse direction. So when you're doing a chemical reaction, you may find that the reaction that you want to do has something on the right-hand side, and if you need it on the left-hand side, simply reverse it. Rule 2 is kind of basically the same as Rule 1. It's simply saying is that products always appear on the right. So if you've got a list of chemical reactions to choose from, you can automatically orient 2 of them to make sure that products are on the left and right. We have intermediates in which they have to appear on both sides. To cancel. It's kind of like terms in a math equation. If you have something on the left-hand side of a reaction and you have the same thing on the right-hand side of the reaction, then you can cross it out. In our Bohr-Haber cycle, what we did is when we were summing up all the reactions, anything that appeared on both sides gets canceled out. The other one is also a restatement of what we've said earlier. Basically, if we reverse a reaction, then we have to reverse or change the sign of the delta H. So reverse the sign of delta H. And then last but not least, remember that we have to multiply the delta H values by the coefficients of the reaction. Meaning if delta H is written for 1 mole and we want to use 2 moles worth of stuff, then we have to multiply it by 2. So let's take a look at an example. So for most of these examples, we're given the question, which is simply calculate delta H naught of reaction for something. And so in this case, we're going to do 2NO2 gas goes to form N2O4 gas. And then we're given a choice or a set of reactions to use. So for instance, we're given that we know that 1/2 of a nitrogen molecule plus an oxygen molecule goes to form NO2, and we know that delta H for that reaction is 33.85 kilojoules, and we'll call that reaction 1. And we know that reaction 2 has N2 gas plus 2 O2 gases, reacts to form N2O4 gas. And the delta H for that reaction is 9.66 kilojoules. So notice if I take a look at those two reactions that, I need to be able to sum those together to make the final reaction. So notice that NO2 is a reactant, right? So that means that down here in reaction 1, I need to write the reverse of that. And also note, so I'm going to write the reverse of reaction 1, so kind of a minus reaction 1. And also note that I need 2 moles, and so I need to multiply it by 2. So I'm going to write the reverse of reaction 1 multiplied by 2. So NO2 gas goes to N2 gas plus 2O2 gas. And I need a 2 here. Apparently I left that 2 out in my notes, but since we're multiplying by 2, I think it's fairly obvious that it's there. So what I did is I multiplied that reaction by 2. And that means for the delta H value, I need to, first of all, reverse the sign, and then I need to multiply it by 2 to get the amount of energy change. And then note for the second one, for reaction number 2, I can use that in the direction it's done or written in, because notice that the NO2 is on the right side of the equation. So now I'm going to take just reaction number 2. This is reaction number. And so this is reaction 2. And I've got N2 gas plus 2O2 gas goes to N2O4 gas. And since we didn't do anything to that reaction, it just stays as 9.66 kilojoules. And then notice that I need to cancel out all my intermediates, meaning I need to make sure that the nitrogen and the nitrogen cancel, that the oxygens and the oxygen cancels, and so that the only thing I have left is the reaction that I want. And then with the delta H values, we just sum them all up, and I should get minus 58.04 kilojoules. So Hess's law is quite useful sometimes if you have a series of reactions that you already know the answers for, and you can combine those reactions together in order to get a reaction that you don't know. Okay, one last example, and then I think we'll call it quits. And actually, I'm not sure, but that's almost the end of the chapter. Normally I break this up over 2 days, but normally I'm not talking to myself the entire time. So we'll see. We might have just a work day on Tuesday to get everyone, no, we got lab to finish. We'll see how it goes. We might just have a work day to get, to answer questions on the homeworks and stuff that people do over the weekend. And if no one does any homework, maybe I'll just lecture that day on whatever next chapter is. So here's a good one, a tougher one. We want to know the delta H of reaction for 2 carbon plus 2H2 gas, and that's a solid, going to C2H4. And actually, I don't think I bothered writing many states down. And our choice of reactions are, reaction 1 is carbon plus oxygen goes to CO2. The delta H for that is minus 393.5 kilojoules. We have reaction 2 that's C2H4 plus 3O2 goes to 2CO2 plus 2H2O. That really is simply delta H of combustion because that's a combustion reaction. We know that that's minus 1410.9 kilojoules. And then we have hydrogen gas plus half an oxygen gas goes to form water. That's our pretty standard reaction to make water. Delta H for that is minus 285.8 kilojoules. So the idea is we need to take and use those three reactions in some order in order to solve it. So does anyone have a guess where we should start? I usually like to start with getting the reactants and products on the right side. So for instance, we notice that C2H4 is a product, right? But in the reaction down here, it's written as a reactant. So that means I know I need to take the reverse of that second reaction. So I can simply write the reverse reaction as 2CO2 plus 2H2O goes to form C2H4 plus 3O2. And then I need to reverse the sign of the delta H2, which means it's going to be 1410.9. So a positive value now. Then I also know that I need to get the carbons on the right side of this reaction. Notice that this is one of our reactants. This is a reactant. Notice it's already on the right side of the reaction, right? What do I have to change about it? The reaction down here has one carbon. I want two of them, right? So I'm just going to take 2 times reaction number 1, and I don't even need to reverse it. And so I've got 2 carbons plus 4 H2s. Wait, I'm sorry, I'm looking at the wrong reaction. Plus 2 O2s goes to form 2 CO2. And if I do that, then I need to take 2 times the delta H value. So I need to take basically 2 times minus 393.5 kilojoules. I'm leaving the kilojoules off because, frankly, I ran out of room on the screen. I'm lazy. So we can already see some things happening. For instance, we can see that some of our oxygens are going to cancel, right? And we can see that our CO2s already cancel, so that's kind of nice. But we also need to realize that we need our other reactant on the reactant side. So if I need 2 H2s, I also need 2 times that second reaction, right? So I need 2 times reaction 3. And so if I take reaction 3, that's 2 H2s. Plus a half of an oxygen times 2 is simply 1 oxygen. Goes to 2 H2Os. Ooh, we kind of ran out of room. So I need to take 2 times that delta H value. That's just 2 times minus 285.8. And then if I add those reactions together, I should see that everything cancels out. For instance, I have 3 O2s here. Well, I've got 2 here and 1 here, so I can cancel them out. I've also got 2 waters and 2 waters. So the only things I have left, and maybe I'll write it in red just to highlight it, is, I've got 1 reactant, I've got my other reactant, and then I've got my product. So I've got 2 carbons plus 2 H2s go to a C2H4. And then if I sum up all my numbers over there, I better get minus 52.3 kilojoules. And I only say I'd better get it because, I know the answer. I wrote it on the piece of paper. I've done the math. What you should do is probably double check all of that sort of stuff. Certainly you never know when I make a mistake, and it's good practice. So that's, I think, it for Chapter 8. I'll check through some things. And so what we're looking at is Monday, Tuesday, Wednesday, Thursday, Friday. On Tuesday, we want to have homework. I believe, are we at 8? Did we do 8C already or not? Certainly it's all due at that day, basically. But I thought 8C was due earlier, but for sure D and E. Oh, we have 2 last topics that we'll cover Monday. Oh, we got a lot more. I forgot, this chapter is bigger than I remembered. Yeah, and we have the thermodynamics. So I guess just C, D, and E for sure. And I'm pretty sure D and E were actually, or C was actually due Friday. And then on Monday, we'll, of course, lecture. We'll finish the calorimetry lab. we'll lecture/review. And then I don't know what days we're going to put the test, but it's going to be over chapters 7 and 8. And I'm leaning towards putting the test on Friday and then having Thursday be that last chance to get all your homework back, to review, to ask any questions that you want, to take the test on Friday. It's a very good breaking point for us because, of course, after next week it's Thanksgiving, right? And frankly, taking a test after Thanksgiving over material you covered all before Thanksgiving is the worst thing ever. As far as I can tell, turkey makes everyone stupider. I think I've mentioned that before, that you just forget so much stuff. I'll probably even forget people's names. Definitely Nathan's name I'll forget. He's not terribly memorable to begin with. Gabe, I might remember him because I like him. He's a nice guy. And how many Gabriels do you really know in life? Are you shitting me? Wait, from the dad before the one your mom married? So he's your stepbrother.
He's a half brother. My real dad's son, his name is Gabe.
Did your mom know that when she named you Gabe yet? So